Okay, I want to try a little experiment on you. I'm going to describe a person, and you tell me if I sound like a human or, I don't know, a malfunctioning robot. Ready?
I'm ready. Lay it on me.
All right. She is a charming young blonde lady.
Sounds perfectly normal to me. I can picture her.
Okay. Attempt number 2. She is a blonde young charming lady.
Oof. No. That physically hurts my brain a little.
Right.
It's the same words, but it just sounds broken, like you've just started learning English yesterday.
It gives you this weird cognitive itch. And the crazy thing is, most of us, most native speakers, have no idea why the first one works and the second one is just so wrong.
We just know it is.
We just know. But there is a rule, a very strict, invisible rule.
It's the royal order of adjectives.
The royal order, I like that. You know, opinion before size, size before age, age before color. It's this whole complex hierarchy we just obey without thinking.
It's one of those things that proves language isn't just a bag of words we throw around.
It's a structure.
A deeply ingrained one.
And that structure is the nightmare scenario for today's Deep Dive. Because we are looking at how on earth you teach a literal rock we tricked into thinking to understand that same cognitive itch.
And just to make it even harder, we're not talking about English today.
No.
We're looking at this fascinating paper from the Indian Institute of Technology in Kharagpur, and it's all about Bengali.
The paper is titled Prenominal Modifier Ordering in Bengali Text Generation, which I know sounds a little dry.
It does sound a bit academic.
But I promise you it's basically a detective story about how to make AI sound less like a calculator and more, human.
It really is. The researchers were trying to solve a core problem in what's called NLG, or natural language generation.
So when a computer writes a sentence...
Exactly. When a computer writes a sentence in Bengali, how does it know which adjective comes first?
And I think we need to establish the stakes here, because my first thought was, who cares? If the computer says red big ball instead of big red ball, we still get it right.
In a simple case, sure. But imagine you're reading a news summary generated by an AI, or worse, a medical translation.
Okay, yeah.
If the ordering is off, the fluency just breaks down. You stop trusting the text. It increases the cognitive load, meaning you spend more energy trying to figure out the sentence than understanding the actual meaning.
It's the difference between a smooth conversation and a puzzle you have to solve.
Exactly. And Bengali presents this really unique challenge. In linguistics, we often call Bengali a free word order language.
Which sounds like you can just throw words in a blender and pour out a sentence?
To an extent, yeah. For the big parts of the sentence, the subject, the object, the verb,
yeah,
you have a lot of flexibility. But, and this is a really big but, inside the noun phrase,
the specific chunk describing the thing.
right, inside that little bubble, the rules are actually quite rigid.
So you can move the big red ball all over the sentence, but you can't mess with the big red part.
Precisely.
Yeah.
And if you do, you don't just sound awkward, you can sound completely incoherent. The paper has this great example. Nanarakama Bichitra Samudrika Pranay.
Which means many peculiar sea creatures.
Right. It flows. Nanarakama, many, Bichitra, putra, peculiar Samudrika, sea. It has a rhythm. But if you scramble it, say Bichitra Samudrika Nanarakama Prani,
it just crashes.
It crashes. Peculiar sea, many creatures.
That sounds like a bad Google Translate result from, 2010.
It really does. So the researchers at IIT Kharagpur, they set out to teach a machine how to avoid that crash. And they ran into a wall almost immediately.
The wall called data sparsity.
Exactly.
This was the part of the paper where I actually felt bad for them, because they started with a huge data set, didn't they? The CIIL corpus.
Yeah, it's a big one. The Central Institute of Indian Languages corpus, it has about 2.21 million tokens.
So 2.2 million words.
Basically, yeah.
In my head, that sounds like more than enough. If I read 2 million words, I'd be pretty fluent.
You'd think so. But here's the problem with learning adjective order. To learn the rules, the computer needs to see examples with multiple adjectives.
Right. It has to see them competing for the same spot. It needs to see big red ball.
If it just sees red ball over and over, it learns nothing about ordering.
So they filtered these 2.2 million words looking for noun phrases that had 2 or more adjectives.
They did.
And what did they find?
Well, out of nearly 130,000 noun phrases, only 4,651 had more than one adjective.
Wait. Say that again? Out of 130,000 phrases, only 4,000 were actually useful.
A little over 4,000, yeah. It comes out to about 3.6%.
3.6%. That's nothing.
It's a needle in a haystack. A very, very large haystack.
So they're trying to build a comprehensive rule book for a complex language based on 3.6% of the available data. It's like trying to learn the rules of traffic, but you're driving on a deserted highway 96% of the time.
That is a perfect analogy.
You never learn who has the right of way because you never see another car?
And because that road was so empty, the standard approach, what they call the baseline model, it just failed miserably.
Let's talk about that failure, because it really sets up how clever the solution is. They started with a big room model.
Which is the simplest way you can do this. A bigger model just looks at pairs of words.
Yeah.
It asks, how often is word A sitting right next to word B in my data?
So it's just counting. I've seen peculiar sit next to C 10 times, so that must be a strong connection.
Exactly. But think back to our empty highway. Because the specific combinations were so rare in the text, the model had almost nothing to count.
It was just guessing most of the time.
It had high precision, which means when it did make a guess, it was usually right. But its recall, the ability to actually handle new phrases, was awful.
So the final grade was bad.
The final grade, the F measure, was stuck at around 81%.
Now, 81% sounds like a solid B minus to me. Why is that considered so bad?
Because in language generation, 81% means that nearly 1 in every 5 phrases the AI generates sounds like a robot having a stroke. If you're building a translation app, 81% is completely unusable. You need to be in the high 80s, really the 90s, to start feeling human.
Okay, so the simple counting method fails. There's just not enough to count. And this is where the paper gets really, really cool. They realized they couldn't just count their way out of this problem.
They had to think their way out.
They built a 3-stage system. You called it a 3-layer cake of logic.
That's a good way to put it.
So let's break down these layers. Stage 1 is called direct evidence.
This is the most conservative layer. It's simple. It just says, if I have seen big come before red in my training data, I will use that order.
I saw it with my own 2 eyes, so it must be true.
Yes. But, based on your reoption to the data scarcity problem, how often do you think this layer actually had an answer?
Well, given that 3.6% stat, I'm going to guess not very often.
The researchers actually calculated the coverage of this direct evidence matrix. It was 0.07%.
0.07, not 7%, 0.07.
0.07%.
Okay, so that's not a solution, that's a rounding error. That's basically the computer staring blankly at the page 99.9% of the time.
Exactly. It's safe, but it's useless on its own. So they needed stage 2, transitivity. And this is where they start using graph theory.
Okay, hold on. Graph theory, that brings back some bad memories of high school math. Explain this to me like I'm 5.
Okay, imagine a map. Every single adjective in the Bengali language is a city. Red is a city. Big is a city. Good is a city.
I'm with you so far.
Now, the computer wants to drive from big to red. If the data has a direct road between them, meaning it's seen those words together, it just takes it. That's stage 1.
But what if there's no road?
Then you're stuck. Unless you look for a connecting city. The computer might see a road from, say, big to round,
Okay.
and it also sees a road from round to red.
So if big comes before round and round comes before red.
Then logic dictates that big should probably come before red, even if the computer has never ever seen the words big and red in the same sentence.
It's the transitive property. A is greater than B, B is greater than C, so A must be greater than C.
Exactly. And to do this across the entire language, they used an algorithm called Floyd-Warshall.
Which sounds like a law firm.
It does, doesn't it?
Yeah.
But it's a classic path-finding algorithm. It's used in things like GPS navigation. It looks at the whole network of words and calculates the shortest, most logical path between all of them.
So it's filling in the blanks in the map. It's saying, I haven't seen the specific pair, but based on the friends they keep, I can infer the order.
That's it. And that was a huge step up. It took their coverage from that pathetic 0.07% all the way up to about 14%.
Okay, 14% is much better, but it's still not great. That leaves, what, 86% of the map completely dark?
Which brings us to the pièce de résistance, stage 3. Semantic clustering.
The meaning layer.
This is where the AI stops looking at just the words themselves and starts looking at the concepts behind them.
But how? The computer doesn't have a dictionary. It doesn't know that blue is a color or big is a size.
No, it doesn't. So it uses something called the distributional hypothesis. The core idea is, you shall know a word by the company it keeps.
Give me a real-world example of that.
Okay, imagine you're at a party. You don't know anyone's name, but you see a group of people over by the kitchen, and they're all talking about, say, stock options and interest rates.
Okay, I'm grouping them together. The finance bros cluster.
The finance bros cluster, right.
Right.
Then you see another group by the speaker talking about bass drops
Mm.
and BPM. That's your DJ cluster. You don't know their names, but you know they're similar because they exist in the same context.
So in the text, if two different adjectives tend to modify the same group of nouns, the computer assumes they must be similar.
Exactly. If the word wide modifies road and river, and the word narrow also modifies road and river, the computer figures, okay, wide and narrow are probably related. They're in the same cluster.
And they use some fancy math to measure this closeness.
They use cosine similarity. You can think of every word as an arrow shooting out from a center point. If two arrows point in roughly the same direction, the angle between them is small.
So they have high cosine similarity.
Right. Wide and narrow are arrows pointing in a similar direction. Wide and, say, green would be pointing in totally different directions.
Got it. And using this, they grouped all the Bengali adjectives into these clusters, and the results were surprisingly human.
They really were.
I have the list right here. Cluster 3 included Samudrika, which is sea, Prakritika, natural, and Samajika, social.
Those are all types or origins.
And cluster 6 had Natuna, new, Purana, old, and Shalati, current.
The time cluster. The AI figured out the concept of time without anyone ever telling it what time is, just by watching how the words behaved.
That is a little spooky, but very, very cool. So how does this finally solve the 86% gap?
Through generalization. Let's say the computer learns a rule from stage 2. It learns that generally time words come before origin words. Then it sees a brand new pair of words it's never encountered. One word happens to be from the time cluster, the other from the origin cluster. Even though the words are strangers, the clusters are familiar.
So it applies the rule for the whole group.
It applies the rule. Time beats origin.
It's profiling. It's saying, I don't know you, but I know your type, so get in the back of the line.
In a way, yes. It's statistical profiling, and it allows the system to cover the entire language based on the behavior of groups, not just individuals.
So we have 3 layers. 1, I've seen this exact pair before. 2, I've seen their friends, so I can deduce the order. And 3, I know their general type, so I can guess the order.
And when you stack all 3 of those, you finally get a robust system. But you still have one last step. You have to actually build the sentence.
Right, you have all these little rules, A before B, B before C. You need to line them up into a single file.
This is the topological sort step.
Yeah.
Think of it like getting dressed. You have a bunch of rules.
Mm-hmm.
Underwear has to come before pants. Socks have to come before shoes. Shirt before jacket.
But the order between socks and shirt doesn't matter. You can do either one first.
Exactly.
Yeah.
Topological sort takes all those constraints and flattens them into one valid linear list that doesn't break any of the rules. It turns that messy web of logic into a straight line of text.
So the million-dollar question, after all that, did it work?
It worked significantly better. The proposed model hit an F measure of almost 88%.
So 87.93% compared to the 81% from the baseline.
Yes.
Okay, I'm going to play the skeptic for a second. That's about a 7% bump. We went through all that, graph theory, cosine similarity, for a 7% improvement.
I love that you asked that because in the world of AI, 7% can be the difference between a research prototype and a usable product.
Really?
Think about the long tail. The first 80% is easy. It's the big obvious rules. Red usually comes after big. A simple calculator can get that right. But that last 20%, that's where all the weird stuff lives, the exceptions, the nuance, the poetry. Clawing back 7% from that territory is incredibly difficult. That 7% is what makes the AI sound like a native speaker instead of a tourist reading from a phrase book.
It's closing the uncanny valley of text. That 7% bridges the gap.
Exactly. And there was one more comparison they did in the paper that, for me, is the most important part of this whole deep dive.
What was that?
They compared their Bengali model against a very famous English model created by a researcher named Mitchell.
Mitchell's model is basically the gold standard for English adjective ordering, right?
It is. And when they ran Mitchell's model on the Bengali data, it struggled. Its recall was much lower.
Why? I mean, if it works so well for English, why not for Bengali?
Because the two languages have, and this might sound weird, fundamentally different philosophies about ordering.
Philosophies.
Think of it this way. Mitchell's English model relies on what are called positional classes. It assumes adjectives have assigned seats. Size always sits in chair 1. Color always sits in chair 3. It's very rigid.
It's like a seating chart at a formal wedding.
A perfect analogy. But Bengali is less about where you sit and more about who you're related to. It's relational. It's not about chair 1 versus chair 3. It's about relative dominance. Is this word semantically closer to the noun than that word?
So the English model was looking for a seating chart in a room where everyone was just mingling based on their social circles.
That is a brilliant way to put it. The English model tried to impose a rigid grid on a fluid relational system, and it failed. The IIT model worked because it respected the social dynamics of the Bengali language through that semantic clustering.
That feels like a massive lesson for AI in general. You can't just build a model for English, copy-paste it to Hindi or Bengali or Swahili, and just expect it to work.
You absolutely cannot. Language reflects culture, it reflects a way of thinking. English logic is often positional. Bengali logic, in this context, is relational. If we want AI to be truly global, we have to stop treating English as the default operating system for human communication.
It's about the democratization of technology. If we don't build these custom architectures, we end up leaving billions of people with second-rate tech.
Precisely. And that's really what this paper represents. It's not just about adjectives. It's about building AI that meets a language where it lives.
So what's the next frontier here? We've gone from just counting pairs to understanding semantic clusters. Can it get even better?
The researchers end with a really fascinating suggestion. They talk about using ontological knowledge.
Ontology, that's a heavy word.
It basically means the nature of being. Right now, our model knows that sea and natural are in the same cluster because the math says they hang out with the same nouns.
But the computer doesn't know what the sea is. It doesn't know it's wet or that it's salty or that it's huge.
No, it's all just statistics. But imagine if we could plug this system into a true knowledge base, an ontology, a database that actually understands that a sea is a type of body of water, and the water is a liquid.
So moving from probability to actual understanding.
Yes. If the computer understands the physics of the objects it's describing, it might be able to order adjectives not just because of a statistical rule, but because it understands the reality of the scene.
So it wouldn't say a broken glass heavy vase because it would understand that heaviness is an inherent property of the vase and broken is a temporary state applied to it.
Exactly. And when we get there, the line between human writing and machine writing might just disappear completely.
That is equal parts exciting and terrifying.
That's the definition of progress, right?
Well, next time you correct someone's grammar, just remember, you are running a massive graph theory algorithm in your head, cross-referencing semantic clusters and calculating cosine similarity, all in a fraction of a second.
The human brain is still the best computer we have.
For now, thanks for listening to The Deep Dive.
Keep learning.